Hi, in this presentation today, I am going to review the paper Self-supervised Learning for Large-Scale Item Recommendations by Tiansheng Yao et al. At Google Brain. Large-scale recommendation systems are super useful in our daily lives, from recommending songs, movies, restaurants, or highlighting videos. They are touching our lives every moment. These systems help users surface handful candidates out of a very large pool of items ranging in millions and even in billions. For example, when you see a list of videos on YouTube, it is actually fetching data from billions of videos in the pool. This system further has large impact. 40% of app installed on Google Play, 60% of watch time on YouTube, 35% of purchases on Amazon, and 75% movies watched on Netflix comes from these recommendation engines. Now let's talk about the challenges associated to large-scale recommendation system. With millions to billions of items in catalog, only few items or products are popular, and users tend to provide feedback for a very small set of them, causing a power law distribution. This makes feedback data for long tail extremely sparse. Also, these long trails of items goes unused because of label sparsity problem. Further, recommendation systems are designed over these popular items and hence they become biased. Therefore, this poses a question on the fairness of the recommendations. Input space for these models are large vocab categorical features, and designing systems with high dimensional categorical feature is always challenging in machine learning world. Let us discuss some of the related work which has been influential in formulation of this paper. The foundation of the model architecture is influenced by deep learning, which has led to many successes in building industry-scale recommendation system. For large-scale item retrieval, two tower models with separate query and item towers are widely used due to its high efficiency for serving. To address label sparsity problem, this research work has considered SimCLR paper. This paper proposes a self-supervised and a contrastive learning-based technique for visual representation learning in the area of computer vision. We will later discuss how the same technique has been adapted for recommendation systems. To support SimCLR architecture, which requires image augmentation, this paper proposes a two-stage data augmentation process, which is tailored for categorical features, which is one of the challenges discussed in the previous section. Now, let's discuss about these influential work one by one further. Two-tower model forms the base foundation layer. It is one of the most popular neural network model for recommendation system, where two deep neural networks referred to as towers act as encoders to embed high-dimensional query items features into a low-dimensional space. It takes advantage of learning capabilities of neural network to extract informative representation of covariates in a nonlinear fashion. A key advantage of this model is that it is able to tackle the long-standing cold start issue by incorporating features to produce accurate recommendations for brand new items. This figure represents the two-tower DNN model, wherein the first tower, the query tower, which actually translates the query features into a query embedding space. The other tower, which is the item tower, wherein the item features are translated into item embeddings. and then the whole network is further trained on unsupervised loss. Another influential work considered in this paper is related to self-supervised learning. Self-supervised learning is a type of unsupervised learning where the data provides supervision or label. It has shown extensive success in the field of computer vision and natural language processing. Here, self-supervised learning is implemented as SimCLR architecture. It's a simple framework for contrastive learning of visual representation. Let's try to understand the whole architecture from the diagram on the left. In here, we have two different samples, a sample of a dog and a chair. The next layer actually does the augmentation, wherein two different augmentation of the sample is created. Then these augmented samples are translated using a CNN and an MLP layer. Further, the loss function is created in such a way that the similar examples try to attract while the dissimilar objects try to repel each other. Also, the same is represented on the view on the right in a more methodological format, wherein an input is transformed into different representation using the augmentation functions, and the maximization or minimization of the agreement is taking place. Below represents the loss function, wherein the numerator is something wherein we are trying to maximize the agreement, because in there we are considering two similar objects, and in the denominator we are trying to minimize the agreement wherein the two dissimilar objects are being considered. The generic representation, which is learned by simultaneously maximizing and minimizing the agreement, and this whole methodology is called as the methodology of contrastive learning. Updating the parameter of a neural network using this contrastive objective causes representation of the corresponding views to attract each other, while representation of non-corresponding views tries to repel each other. As discussed, in CMCLR model, we are required to create two augmented examples for a given sample. The augmentation becomes a very important step here, and we need to perform a good transformation and data augmentation. These functions should make minimal amount of assumption on the data such that it can be generically and generally be applicable to a large variety of tasks and models. This idea of translation augmentation was inspired by mask language model in the BERT architecture. The two different kinds of data augmentation function considered in the architecture are masking and dropout. There are two different masking techniques which are further being explored. One being random feature masking, wherein the features are masked randomly, and another technique being correlated feature masking, where the correlated features are masked together at the same time. In case of the augmentation using dropouts for categorical feature with multiple values, each value is dropped within certain probability. This actually helps in further reducing the input information and increasing the hardness on self-supervised learning task. Let's try to understand the masking in more details with an help of an example. The original feature represented here are the features of an app, wherein you have an app ID, the app title, and app tags detailed here. With the help of augmentation functions, we translate the original feature into two examples. One wherein the tags is masked totally, and in the other case wherein the app ID and app title features are masked. In case of the random feature masking, these features are masked on a random basis. But in case of the correlated feature masking, the correlation between two features is first of all calculated and the correlated features are masked together. With the pre-computed mutual information, the paper proposed correlated feature masking that exploits the feature dependency pattern for more meaningful self-supervised learning tasks. For the set of masked feature, mask sees highly correlated feature together and accordingly it masks the feature in the system. Now let's try to understand how all the influential work which we have discussed previously combines together to create the end-to-end model architecture for this particular problem set. Architecture here leverages two-tower model or two-tower architecture wherein the query features and the item features are translated to the respective embeddings for query and items in two different towers is clearly represented in the diagram here. Further, to get the self-supervised architecture implemented, we see that two augmented layer is being created wherein the two augmentation of the features are created using masking and dropouts and a respective self-supervised loss is trained on top of it. To enable self-supervised learning based learned representation to help improve the learning for the main supervised task such as regression or classification, a multitask training strategy is performed where the main supervised task and the auxiliary self-supervised task are jointly optimized. In here, we represent the loss function of the main supervised loss and the loss function for the self-supervised loss, how these two combine together to create the loss function for the whole network. This network actually utilizes the training data, the data which is sampled from heterogeneous dataset. Labeled dataset coming from the popular item is used to train supervised system, and for self-supervised long trail data is being utilized. The joint loss is calculated using the formula shown where the L main is the loss function for the main task capturing interaction between query and item and is further calculated as bash softmax cross entropy loss. Alpha here represents the regularization strength and L self is contrastive loss discussed in the previous section. The architecture discussed is further being experimented on two different datasets. One dataset being the Wikipedia dataset, wherein the goal is to predict the set of pages that are likely to be linked together to a given source page from the whole corpus of web pages. Each page is represented by a feature where all the features are categorical, one hot encoding of page URLs, bag of word representation of the set of n-grams of page title, and a bag of word representation of category that the page belongs to. The other dataset which was considered is from app-to-app installation problem. The goal here is to recommend highly similar apps given a seed app. Features were application ID, which is one hot encoded, the developer name, the application categories, title unigrams. So what this suggests is all of these features were like massively categorical features. There were different experiments which were conducted and the model performance were compared against three different baselines. One being a two-tower deep neural network, second being a random feature dropout over supervised learning task, and third, spread out regularization on the item tower. It was observed that the framework proposed by the current paper superseded and outperformed all the other baseline models. Both a qualitative and a quantitative analysis was performed. In case of the quantitative analysis, the MAP and recall values were calculated, and the results shows that the proposed method outperforms the baseline. And with the help of a visual representation as well, the results were evaluated. And what we see from the outcome is the similar objects, the similar items has the same vector space, and they were segmented in the same vector space, which is clearly evident from the visual representation here. To conclude this whole study, what we have observed is the self-supervised learning improves the model performance. Relative improvement is larger for self-supervised learning when the training data is sparse. Also, the observation tells us that this approach improves more on tail dataset, where the training dataset is sparser compared to head. Self-supervised learning for large-scale recommendation research work provides a state-of-the-art implementation for building the recommendation system. It solves for all the major problems faced, which we have discussed earlier. The cold start and performance of the serving is solved using a two-tower modeling technique. Label sparsity and fairness issue is addressed using self-supervised and contrastive learning technique. Categorical features are addressed using augmentation technique. These models, being both performant and solves for all the major problems, can be further deployed both in batch and real time. Thank you everyone for your time reviewing this work. In case if you have any question, please reach out to me on my email address shown here. Thank you so much. Have a good day.